All right, we've got Simon Shack back in Grimerica after, I don't know, maybe a year or two, I guess. But Darren was over there visiting in person, checking out the model and talking to you guys about it. So we thought we'd have you on and go over it again and see what's kind of new. And I think I'll kind of let you guys kind of run with it because you guys are kind of more up to speed on me than me on this one. So I think we're just going to talk about, sort of give it an overview and then get into some of the, like, there's three or four special aspects that Darren wants to address.
Sure. Well, I think the main thing is just getting the slides. I mean, people might want to seek out the video on this one. There'll be a link to it in the show notes. But
go to tychos.space, right? Tychos.space to follow along.
You can get the book for free.
Yeah.
You can play with the model there for free. There's a free PDF of the book you can download. And you might just want to download the video, because the main reason I think I wanted to do the show again, too, is because last time we had the model in front of us and we were talking about it, but they're all kind of, the slideshows really come a long way in the last year. And I feel like the slideshow really sort of ties it all together. It really is. It makes us, they're kind of big ideas that are this all sort of theory that people don't really, it's hard to visualize already, all of it. So I think that the slideshow that you had put together when we met in England, I think had really sort of starts to hit it home. So I wanted Graham to see that, for one, and sort of take the listeners through that as well. So I would encourage people on this one to go to YouTube or Rumble or Rockfin or Locals or wherever. And
we're having a problem. Speaking of that, we're having a problem with Rumble right now.
I just noticed that, but either way, the video will end up there. So yeah, check it out. This, like I say, this one that we're really going to be video heavy on this, so it's a good one to check out. But I mean, you could get something from listening to, especially if you already know a little bit about the model.
Yeah, so it was fantastic, Darren, to see you coming to England. I really enjoyed it.
Yeah, it was a beautiful spot that you guys had for that thing. It really was something else.
Yeah. Nigel's Wonderland, I call it, in the middle of the countryside. And it was a nice weekend, I think. We had a good time. And I found there were 6 people coming from across the pond for the event, including you,
including me. Yeah, there was a lot of international travel. I mean, I was surprised to see that many people come over from this side, but it was a nice trip. It was beautiful, and it was nice to meet all you guys and get the signed copy of the book. And it was great.
Yeah, I was really happy. It went well. And so what we're going to do a little now is maybe I'll select a few slides, the same I used in England, to just do a summary of for newbies to the Tychos model. And so the Tychos model is based primarily on Tycho Brahe's model. Tycho Brahe was a very great astronomer, maybe the greatest observational astronomer of all times. And he was a Danish guy who was a friend with the Danish king, so he got had a big castle on an island in southern Sweden. And he, for all of his life, he looked at the stars. He made the best tables ever made. And then later on, he met Kepler, and Kepler came and kind of, because Brahe had determined this system we're looking at now. You're seeing this slide here right now, are you?
Yep.
So this is, what are you seeing? Is precisely the model of Tycho Brahe, but with one exception, one extra thing. And what I've called the PVP orbit here. And that's because Tycho Brahe had this system devised. He actually concluded that the sun, which is the orange thing here, and Mars go around like this in intersecting orbits. Their orbits intersected, and which is a signature of any binary system. We know now that binary systems are ubiquitous. How do you say ubiquitous? Ubiquitous.
Ubiquitous.
Ubiquitous. Thank you. In the skies. I mean, there are so many astronomers that have been looking up now that have been saying this for years, that it looks like all the stars have a companion. So logically, we should have one as well. Why would the sun be the only single star in the universe? Since everyone else has, all the stars have they're like husband and wife. So what I was saying before, the PVP orbit is the extra thing I've added to Tycho Brahe's excellent model. He was excellent because he was accepted for 100 years after his death. It was a ruling model. Most people don't know that. After he died in 1601, it was accepted for at least 100 years. Before Copernicus came, I mean, somehow the Copernican system took over. So it's a mystery how that actually happened, because it was the best system available at the time. But what the problem was that he thought the Earth was immobile. The Earth was here immobile, not moving, which is a bit illogical, because we know that every single body in our universe has an orbit of its own. Every single body we see in the skies has a small orbit of their own, including all the stars have orbits of their own. And no one tells you that. No one tells you that. Very few people know that the stars, they're not. We have no example of a star which is fixed in the middle of a system which has planets rotating around it. There is no such example in the skies. All the stars rotate around a companion. And in this case, it is Mars. In our case, it is Mars. Mars is going around the sun. So let us read this. In the Tychos model, the Sun and Mars are a binary pair circling around each other at a 2-to-1 rotation ratio, approximately 2-to-1. The Earth revolves around its PVP orbit in the opposite direction, thus accounting for the equinoctial precession and the alternation of our pole stars. We'll get there later to explaining the precession. But it's very simple. Since Earth is moving around this way, in 25,000 years, it will complete this blue orbit. We will change, our North Stars will change, because we're moving physically. We're moving. We're not wobbling, we're moving. Then Venus and Mercury are the moons of the sun. I mean, I'm the first one to say this, but it's absolutely logical that they are the moons of the sun. Why? Because Mercury and Venus, first of all, are the only planets we know of in our system that have no moons. And that's a mystery for astronomy. Why don't they have moons? Venus and Mercury don't have moons. Also, they are the absolutely slowest rotating bodies. They rotate at walking pace. Venus rotates around its axis at 2.7 kilometers an hour. That's very slow. And Mercury, double, 5.4. And that's very, very similar to our moon, which rotates at 16.6 kilometers an hour. So these are moons. The definition of a moon is that they rotate very slowly around their axis, and they always keep the same face facing their host. So Venus and Mercury always keep the same. If you were on the sun, you would always see the same face of Venus and Mercury. And don't let anyone tell you otherwise. They are saying that, no, it's not quite like that way, because heliocentrism doesn't accept that thing, but it works here in the Tychos. We know, of course, that the moon always keeps the same face towards us. That's because it's tightly locked. It's probably a magnetic thing that makes all these moons always show the same face to us. And it is absolutely officially accepted that the moons of Mars, Phobos and Deimos. Did you know that Mars has had 2 moons, guys? Did you
Yes.
know that?
Yeah.
Oh, you learned that maybe later.
Yeah,
Yeah, yeah.
our first episode was on Mars, like going back
All right.
666 episodes earlier. We talked about the monolith on Phobos.
Oh yes. Well, most people don't know about Phobos and Deimos, really, right? I mean, most people, man on the street. Um, so Mars has 2 moons, Phobos and Deimos. Sun has 2 moons. So it's like a husband and wife having 2 kids, around them. It's as simple as that. And for some reason, we only have 1. Okay.
So for people that are already questioning this, like Tychos, you said he was one of the best astronomers, observable astronomers, and this what you've got is built on observable data too, right?
It is built on all the observational tables compiled throughout the centuries, and even the NASA tables, they correspond to the Tychos. I mean, I've been checking and rechecking and double checking every single position hundreds of years back of each of our planets, and they match up. They check out with observations. So that's very important to say. I mean, this is not just a fanciful idea. No, it actually works. It works perfectly. And why does it work better than the Copernican model or the Keplerian model, whatever you want to call it? I call it the Copernican. The Copernican, I mean, the heliocentric model that we've all been taught at school. It says that the sun is in the middle and everyone goes round, right? Like this, like this. Okay, this is what we learn in school. Sun is in the middle and everyone going around like in concentric circles. Very nice, neat, and simple to understand. Fine, but this model, what I show in my book, that this model is geometrically impossible. 4 reasons that I will expound now. It has much to do with Mars, which was the biggest problems. The biggest problem, absolutely biggest problem that Tycho Brahe had was Mars, and that's why he asked Kepler to help him. Kepler came into his studio one day, and he said, "I can help you resolve the problem of Mars." And Kepler said, "I'll fix your problem in 8 days." He said, notoriously, but it took him 8 years to even come to some kind of conclusion, because Mars was a really, really intractable problem. Why was Mars such a problem? Well, let's jump forward here. Oh dear. Oh dear, I have to remember where I have with the sequence here. No, okay, let's just let me go just slowly back here. So this is the model. Okay, we have the PVP orbit going. So please understand that it's not Earth going around Mars. Mars is not being circled by Earth. The reason why Mars is here is just because it's passing, but it always passes in the middle of the PVP orbit. Remarkably enough, because the PVP orbit that I have calculated is 113.2 million kilometers in diameter, and Mars, when it passes here, it passes just in the middle of this orbit, which was something that I discovered later on in my research after several years. That I realized, well, my goodness, Mars is passing exactly in the middle of my PVP orbit. Is that a coincidence? So the PVP orbit provides the simplest imaginable explanation for the all-important precession of the equinoxes. What is a precession of the equinox? It's simply that we see the whole firmament, all the stars moving eastwards every year. It's like ticking by 51 arc seconds every year. and by a full 360 degrees in 25,344 years. Just imagine here. Do you see my mouse here?
Yep.
Okay. So Earth is going this way, right? Tick, tick. So slowly, very slowly, at a speed of 1.6 kilometers an hour. That's 1 mile per hour for you Americans. 1 mile per hour. That's the speed, the absolute speed in space that Earth is moving.
Well, not just for Americans, for the Egyptians too, right?
Yeah, I mean,
well,
mile
so
per hour is.
I mean, do you want to ask the question, Darren? I mean, how does this not fit with the sacred?
Well, that's kind of what
system,
the mile is sacred all over the world. It was sacred to the Egyptians. For some reason, America, wants to hang on to it. America seems to be, kind of occult, or at the very least founded by Freemasons that are trying to hold on to this information for one reason or another. And then you go to England and they're still using the mile for some reason. They've gone metric on everything, but they just need to hang on to that mile, and the Egyptians had it. And I think it also starts to play into other things, like, because I think 1 mile isn't it like the Earth rotates 1,000 miles an hour or something like that on its on its rotation. So you start to see there's some weird numbers that seem to be baked in. It's the kind of stuff we talked to with Randall Carlson and some of these other guys about. There seems to be these sacred numbers. I mean, one of the big ones is the amount of seconds in a day, and how and the diameter in miles of the sun. Yep. And there's another one with the moon. And I just thought when I kind of bridge that between his work and your work, it seems to make more sense in the Tychos model, because I feel like all of a sudden those aren't coincidences, they're rules. If the sun was 10,000 miles, then there'd be 10,000 seconds in a day. They're intricately tied together it's almost like, it's just the laws. It's the laws that the sun and the seconds are all going to be, I don't know why. I couldn't tell you why, but it seems to me like the Tychos model, instead of randomness, allows a lot more reason for why these coincidences start to happen. Why is there 109 moon diameters between the moon and Earth, and 109 Earth diameters, 108 between the Earth and the sun?
There are so many incredible things, like 400 times. But let me just finish the question about the precession of the equinoxes, because otherwise it will be hard for listeners to follow. What I'm showing here is a classic animation of how they think, heliocentrists, how they think that the precession occurs. So now we are under Polaris, and the Earth wobbles, the axis of the Earth wobbles, and makes us change North stars. Deneb, Vega, and back Polaris. So Polaris, Vega, Polaris. Okay, Polaris, Vega, Polaris. It goes from Polaris to Vega and back to Polaris. So that's accepted. That's officially accepted. They have been able to calculate that this will happen. That we are going from Polaris to Vega and back to Polaris. So that's not a controversy. Has been because the Egyptians knew that 4,000 years ago there was another star called Tuban somewhere here. Okay, so they've been able to calculate this circle section, and so calculates this ring. But they attribute this ring to a wobble of Earth, which is strange, because it should be a clockwise wobble of Earth, while Earth would rotate every day counterclockwise and go around the sun counterclockwise. But in 26,000 years, they say, it will also do a small backwards motion. But that's not needed at all in the Tychos. In the Tychos, as I said, it's this. We are moving. Simply, we're physically moving around. We're always tilted 23.5 degrees towards the sun, 23.4. And we're going around the circle. So that's why we change the northern stars. Here is another graphic to understand. Today, like on June 21, in our epoch now, we will be facing, Gemini on the summer solstice, June 21. 2,112 years ago, we were facing Cancer. And in 2012 years from now, we will be facing Taurus, just because we are moving around this circle, the PVP orbits. Why is it called PVP again? Because we're under Polaris now. We'll be under Vega when we are on the opposite side almost. And then we go back to Polaris. As simple as that. Polaris, Vega, Polaris. Okay. And this is how this is not my diagram. This is taken from official astronomy books. This is how they have they show how we are moving from Polaris to Vega and Polaris. If looking from Earth up on the northern stars, the North Star ring looks like this: Polaris, Vega, Polaris. If you see these arrows here, they show that this is going counterclockwise. But if you would be above and looking down to Earth, it will be a clockwise motion. Understand? Because this is looking from Earth. But if you were hovering in an imaginary spaceship, this ring would be clockwise, and that's exactly what the PVP orbit is a clockwise ring. Okay, so the reason why I've come to a very precise number of 25,344 years is explained in the book. This is the way I have estimated the diameter. It's a bit complex, so we won't dwell on this here. But that's why the book is. That's why I had to write a 320-page book to explain in detail how I came to this.
Which is free at Tychos.space. You could just pause this and go get that right now and go through those and peruse it at your leisure.
Yes. So here again, I mean, here is like you have to imagine yourself in another spaceship coming, towards the side of our system. You're in a spaceship now, and you're looking at our system, which is we are here now in our epoch, leaning towards the Earth in our epoch, 2000, J2000, and in 12,672 years from now, I mean that's half a turn on our PVP, we will be here. So that's why now we have a Polaris as a North Star, and we have Sigma as South Pole Star. But in half a turn, we'll be under Vega as a North Star and a South Star called Columba. And that's not debated. I mean, this is what the greatest astronomers on Earth are predicting. So I'm making this work in a different way. That's all. I'm not inventing anything, or I'm not violating any predictions. I'm not saying you're all wrong. You're all wrong. No, I say you're right, but it's just the geometry. The actual reason why this happens is because of this. It's because we are going around simply in orbit, always tilted towards the sun. I mean, the northern hemisphere is tilted towards the sun and keeps tilted towards the sun all the time. So, and of course, knowing having estimated the diameter, I've been estimating how fast we move, and that's 1.6 kilometers an hour, 1 mile per hour. So, philosophical interlude. I wish to put this for my presentations, to make people relax and think a little bit. Could Earth's snail-paced motion be a key prerequisite for biological life and for any given planet's habitability? I mean, I'm just saying, doesn't it make sense that Earth is a bit special? We have life here, we have oceans, it's completely different from any planet we know of. We are moving very slowly, and that's why life has been able to blossom here. That's why I have, as a symbol of my book, is a snail. because 1 mile per hour is very, very slow.
It does make the idea of an atmosphere a lot easier to comprehend, you know, then this atmosphere is somehow clinging to the planet while it's flying through the ether or through the vacuum at you know, whatever, 90,000 miles an hour, and then it's
No,
like,
no, 90 times the speed of sound. That's what they say. We are supposedly, Darren and Graham, imagine we are told that we are going around the sun at 107,000 kilometers an hour. That is Mach 90, 90 times the speed of sound. And we wouldn't even notice that. Okay, all right, okay.
well, the crazy thing about that to me is just like, I feel like the night sky would have to change more noticeably.
Also, and that's something I always forget to say. Sorry, I didn't want to interrupt you. There would be, since they Kepler says that all planets slow down and speed up as they go around in circles. We would change our speed by 3,000 kilometers an hour. That's a big change. You know, we always say, "Oh, we don't feel the speed because it's constant." Well, no, they're not saying it's constant. They say it's a variable. It changes. We slow down by 3,000 kilometers an hour. That's like, you know, our fastest jet planes go. You know, jet fighter planes. And we wouldn't notice this acceleration and deceleration over here. Okay. Anyway, about the ubiquity, did I pronounce that well?
Yes.
About the ubiquity of binary stars. Okay. What have we discovered in later years? Because many people say, oh, Simon Shack is bringing up old stuff that has been debunked many years ago. No, the Tychos book would not exist if all these modern discoveries had not been made. I could not have made the Tychos like 20 years ago. We have, in the last decades, we have discovered with better instruments that, you know, a star that looked like this 20 years ago, now they discover it's two stars. Because with adaptive optics is a very sophisticated technique they have to, you know, to be able to resolve better a point of light. So, and they keep finding that many stars they thought were single are double. They keep doing that every single day or week. We have new binary stars. So, could 100% of the stars be double? Yes, I think so. And people have said that before me, like James Jeans, he was saying that many years ago. Many eminent astronomers have started thinking, "Hey, is our sun the only single star in the universe? I'm not the first one who has asked this question." You know, if you know, this is like a cartoon, a funny thing I made. If we were like the heliocentric model was like this, with the sun in the middle and all going around in carousel, like, you know, like a merry-go-round, then the universe would look like this. All of the others are binaries. You know, this is a binary system. Binary, binary, and we would be the only one who is not binary. You know,
With an unexplained wobble that, I mean,
with an unexplained wobble.
You're definitely not the first person to allude to that being from some sort of a binary system instead of a wobble. I feel like when things start wobbling at the speeds they're promoting, they kind of just rattle themselves apart.
That wobble has been disproved, by the way, in later years by different independent researchers, very competent researchers. For instance, you know, the Binary Research Institute of Walter Cruttenden, but many others too. Japanese researchers, they have shown, they've been able to show that the wobble doesn't exist, because if it did exist, it would also change the relationship of our planets in relation to the stars. But that's not observed. It's only the stars that change. It's only the northern star that's changed. But that we should then have a similar, actually a stronger difference of the heights, you know, in the sky of our planets, and that's not observed. So there is no wobble. There is no wobble. Now, this is what astronomers observe today. Again, to say that the Tychos works with modern discoveries. It's not, bringing back some old ideas like many tell me, the naysayers. No, I'm using modern things to back up the Tychos. This is what they see when they look at stars, that have objects rotating around them. Exoplanet, they call them. They call them always exoplanets. They never say we have discovered another star with another companion. No, they say we have discovered an exoplanet. Well, how do they know if it's an exoplanet or another little companion like Sirius B, as we will get to soon? Well, they all go like, inspire graphic things. They do all these funny things. Well, what do we have here? This is what the Tychos model looks like. It looks very much like this, right? In a way. I mean, they're all different in different ways, but they all inspire graphic emotions. So let us now take a close look at the very brightest star in our skies, Sirius. Sirius A is the biggest star we have in the sky. Only in 1862, that's not very long ago, they discovered that it had a companion, very small, Sirius B, they call it now. So Sirius is a binary system composed of Sirius A and the tiny Sirius B. When the latter was discovered in 1862, it caused a huge stir among the world's astronomers. Why? Because they couldn't, it made absolutely no sense within Newtonian theory that such a small thing would be a companion of a much larger star. Actually, 205 times larger than itself. 205 times larger. Okay? Okay? 205 times larger. All right. So do you know what? The sun, is 205 times larger than Mars. And I'm saying that Mars is the companion of the sun. And it just happens that Sirius, the big star, the biggest star in our sky, is 205 times bigger than its companion. All right. Is that a coincidence? Maybe? Okay. Maybe you can say it's a coincidence, but that's what it is. I mean, we're talking now about the diameters. The observed diameters, which are not contestable, they can, they can see the proportional relationship between a star and a smaller star. They have very good telescopes now, and this has been determined. But no one has pointed out that this proportion is the same as the Sun and Mars. That's first pointed out by Simon Shack in 2015. I was the first one who just pointed this out. I didn't discover it. I just said, no one has pointed this out. My goodness. All right. So how did astrophysicists eventually justify the shocking discovery of the tiny Sirius B, which they call the pup because it's, like a small dog? Here's how. They determined, they said, finally, because they were completely, it was a chaos in astronomy circles. They didn't know how to explain it. So how did they explain it? Well, now they explain like this, still today. On Sirius B, the force of gravity is 400,000 times stronger than on Earth. My goodness, this guy his jaw is dropping because why would this be? Newton became famous because he said that physics worked the same everywhere in the whole universe. Well, this is in total contradiction. So, but the similarities between the Sirius system and our solar system do not end here. And that's what I have integrated in my new book, second edition, because my first book came out in 2018. I hadn't come that far at the time. But in 2023, I released this diagram. And you please look at this diagram. Please do understand what this is my favorite diagram, I guess, in the book. So I'm saying here, is the Sirius binary system the twin sister of the Sun-Mars binary system? Well, look at this. To the left, we have a diagram from official astronomy literature. The only thing I've added myself is the elusive Sirius C, because there have been studies that say that there should be a third body. It's a French very big study that's determined that yes, there is probably a Sirius C. I will explain this later. But look at Sirius A and B. If Sirius C is here in the middle, it would be just like Earth. It would be in the middle between the motions of Mars and the Sun. And what is this 1 to 7? Well, that's the distance that we know that Mars comes at the distance of 1 sometimes when it comes closest, and at the distance of 7 from Earth. We know that this 1 to 7 ratio is absolutely, no one can. Everyone knows that. I mean, all astronomers know that Mars does, in fact, do this incredible, comes this close and comes this far from Earth. Well, here we got the same thing happening with Sirius B in relation to Sirius C and Sirius A. It's like too far. You can superimpose them on each other. It's like a photocopy. Our system is a photocopy of Sirius, and vice versa. You understand the importance of this graphic, which was, one of my later discoveries. This is how it actually looks according to official astronomers. This is the Sirius system, and this is how it looks in the Tychosium in the simulator, which we will look at later. We have done a simulator with Patrick, a Swedish computer programmer, which simulates the whole system, and it works very, very well.
Is Sirius C accepted to be a planet and not a star?
Oh, so it's not even accepted quite yet, but it's like controversial right now.
Oh, okay.
Sirius C is controversial because it's not. They say it's probably too close to the big star, Sirius A, to be visible. It's blinded in the glare of the big star. Like
Earth would be, maybe, if we were over there.
Yes, if we were over there, you probably not see Earth, which is a very darkish thing because it's lots of oceans, dark blue. So maybe there is a Sirius C, and maybe there is life there, but I don't go there. I'm just talking about. I'm just going with geometry here in this book.
Yeah,
not doing any other speculations or fantastic
philosophy.
Yeah, right. But and then so what I'm saying also in the book that our two systems are probably a double system. What's a double system? Well, we know of many double systems in the sky. For instance, the Epsilon Lyrae double pair. They are, you see, a pair of stars, binary stars here, revolving around another pair of binary stars. You see my mouse here? Right. So, and there are so many examples in the sky. There are many double systems. So no one can say that double. What's that? No, we know many doubles. So this would explain why Sirius does not precess like all the other stars, as noted by several other independent studies. Do you know that Sirius, a larger star in the sky, does not precess like all the other stars? It always rises in the same point of the horizon, year after year and century after century, all the time. It has only changed by 4 days since 5,000 years ago. So here's my very speculative. This is a speculative diagram I did, but just for a thought exercise, if you like. Are the Sirius system and our solar system a so-called double binary pair? Well, If the Sirius system is here today, because we are here today, and we see a Sirius system down there. You see this purple line. This is how we are today. We see a Sirius system down there, and we see it going down this in this fashion. It goes down like this, and it is said that we are going upwards in relation to our ecliptic. So it does match, this motion of us going upwards, Sirius going downwards. Well, then there is the big astronomer, very, very famous astronomer called Jean Meus. He predicts that Sirius will become our South Pole star in 60,000 years. So we can imagine then as Sirius comes here, it does this in 60,000 years, and comes below us, and it will become our South Pole star. So, Jean Meus is now 95 years old. I wish I could, contact him and show him this, because this it confirms his predictions. You see, now we have our South Pole star here, but in 60,000 years it will be Sirius. Same angle. See? So that's just a speculation, but it does actually match with what we see today. And we must return to Mars, because Mars is really, We shall now return to Mars and demonstrate how Mr. Kepler's mathematical interpretation of its motions, based on Tycho Brahe's precise observations, was not only flawed but outright fraudulent. Kepler was a fraud. Kepler, the most, hallowed. The most famous astronomer in history, he was a fraud. Because what did he do? He had all the best observations possible from his master, Tycho Brahe, yet he fudged with them. How do we see Mars returning in the sky? So, when I say returning in the sky, you just imagine that you go out in your garden one day and you see Mars being exactly aligned with a given star. Okay, so you will have to wait 707 days to see this repeating again. 707, and then you will wait another 707. For 7 times, you will have to wait 707 days for this situation to repeat itself again. Mars facing a given star, but suddenly, the 8th time, it will return only in 546 days. How can this be explained in the heliocentric system? It cannot be explained. It's a 15-year sidereal cycle of 5495 days, which plays out like this. What did Kepler do? Kepler completely ignored these empirically observable facts and instead averaged the sidereal period of Mars to 687. Yeah, of course, if you divide 687 by, you divide 5495 by 8, you get 687. But at no time, never does Mars return in front of the same star in 687 days. It does this. And the Maya people knew this very strange sequence. So you're now wondering, how is it possible? Of course, you must wonder, how can Mars suddenly come back in only 546 days? Well, this is how an official heliocentric simulator depicts this incredible sequence. So, you have, this is the positions of Earth, this is the positions of Mars, the red ones, and I've chosen a star called Jedi for my control experiment here. Well, according to heliocentrism, it doesn't matter where Earth and Mars line up. It will always point to the same star. Even between number 7 here and number 8 here, which that's 300 million kilometers of lateral displacement, but we will still see the Jedi in front, lining up with Mars. Well, here is instead what our Tychos simulator shows. Our Tychos simulator, which is Patrick and mine, we are just two guys working on this simulator, depicts these same 8 conjunctions of Mars with the star Dana Baljetti. Like this. You see, this is 1, 2, 3, 4, 5, 6. Mars always returns here, including this very special 546 days periods. Why? Because Mars is going around in this spirographic way. Here, I show you why. The 546 shorter empirical sidereal interval, as it's called. Well, it's called like that in very, very few books that talk about the Mayans knowledge, Maya astronomy knowledge. Well, see, if, let's say this is date 0, Mars. Mars is just exiting its retrograde period. So it is just finished to complete a retrograde period. It's a loop, which I show you on the simulator later on. And therefore, when it comes here, it comes back earlier on this line of sight towards the star, because it has just completed one period, and that will make the periods as short as 546 days. Only 1 out of 8 times. You see, 1, 2, 3, 4, 5, 6, 7. When this happens, then we will see Mars coming back in only 546 days. This is the only possible geometrical explanation. There is no other competing model that can explain this. That's why I'm so, cocky about Tychos. It is the only system that works. It really is. And you know what? Kepler, in the first pages of his big book, his magnus opus, he actually showed us this drawing, which was a test he did, he said, but he discarded it. But this, what he shows here, is Mars, a 16-year period of Mars from 1580 to 1596, that's 16 years. And he drew it, pen and pencil. He was a very smart guy, of course, like this. Well, if you open the Tychos, it will draw you this, the exact drawing that Kepler did. The Tychos completely is exactly in agreement with his first idea, which he discarded. You understand? Kepler was a very smart guy. Kepler was a very smart guy, but then he completely lost it.
Or he got compromised.
Or he got compromised, but he had probably, maybe had a contract to make Copernicus win. Who knows? I don't know. I don't want to go there. It's just that the facts are these. These are the facts. This is the only way to explain the behavior of Mars, which was a huge, #1 problem. Yeah, and was always a #1 problem for all astronomers of the time. Back in the times.
Can I show that in the model quickly, or should we?
I can open the model myself here.
Because I just had Mars, like Mars are the only planet showing, for example, and just trace Mars only.
I trace Mars. Like, do you see my screen still, or
yeah, no? yeah? Put it at a year, for example.
At a year, so it goes faster.
Yeah.
There.
Wow, that's really fast.
That's really too fast.
I didn't go quite that fast.
Let's go like this. Let's go like this. Okay. Now, see what Mars does?
There you go. So there's your evenness. It comes around the same amount, right? And then
no, not the same amount. Sometimes less, and sometimes the retrogrades are different for Mars.
Yeah, right.
Very different. And that's also unexplainable in the heliocentric system, because they should actually be larger when Mars is closer to Earth, whereas they're shorter when it's closer to Earth. So, I mean, there are so many problems with the heliocentric explanation for the retrogrades also. But the retrogrades are, I mean, you think you're going to say, why is Mars doing this? You know, the first time you look at this, you say, why is Mars doing this? Well, I take away the trace now, and what is Mars doing? Well, it's kind of, you know, it's going around. It's going around the sun, right? Well, yeah. Well, it's let us first do one thing. I really like this.
Oh, interesting. Yeah,
I
it's
want to show
not
you.
really.
I want to show you Venus. I want to show you Venus. Just concentrate on Venus. I'm going to. Okay, I'm going to switch off Mars. Okay, just switch it off. We don't need to look at it. We get confused.
So this
Just
is
look
how
at Venus.
interactive the model. This is how interactive the model is. You can just take
Yeah.
all the planets out, put them in. You can speed it up,
Yes,
slow it down.
it's
It's quite
beautiful.
amazing to play around.
Patrick has done a fantastic job with this. And you know, you can go close to Earth and see Earth. You know, you can put just 1 hour and see how Earth goes around itself and its axis. It's wonderful. It's beautiful. So, but let's go back now to what I wanted to show you about Venus. So let's now just look at Venus going around the system. We start a system and we see Venus going around, maybe a bit faster.
Okay, hang on. So there's Venus, the one that's going around the sun there, right?
Yeah, this one, the white one. Okay.
Yeah.
Venus is almost the same size as Earth.
Yeah.
But of course,
why they could get confused, because the two inner planets that they observe are going around the sun.
Yeah,
right, Mercury and Venus.
Please understand that the sizes of the planets are not to scale. People are saying, "Oh, Venus comes very close to Earth, as close to as the moon almost." No, this is they're exactly tuned to what they should be. It's just that they're bigger in order to see them on the screen. So anyway, what have you been looking at now? You have been looking at a planet called Venus going around in circles around the sun, right? It always ever goes around in circles. But if I put a trace on it, as if we would light a bonfire on Venus, and the smoke will leave a trace. Well, let's do that. Let's put a trace on Venus. Let's put a trace on Venus and see what happens. Now, I put a trace on Venus. Oops! Oh, look, it goes backwards. Oh my goodness! I shut off Mars. I shut off Mars, please. No Mars. Oh dear. Wait. Stop a second, because Mars. We don't need Mars. We don't need Mars here. That's why. Okay. So let's continue to watch Venus doing what it does. What does it do? It always goes around in a circular motion around the sun, right? But as seen from Earth, it will go backwards. That's a retrograde motion that everyone talks about. And it was the biggest mystery of astronomy was, why do planets regularly seem to go backwards? Because they do. Because that's geometry. It's nature for you. Because an object revolving around another revolving object will do this trochoidal path. That's just the rule of nature, geometry. Call it what you like. All right.
Seems to be like a rule of solar system dynamics. It's like,
no, it's a rule of geometry. You can do a game.
And
the
other interesting thing with this is that you can plug in some dates and it'll predict all the retrogrades moving forward and going backward, and it'll be exactly accurate.
Yeah. Now, would like to briefly show you this. This is an animation I did, which is on my forum, which shows that if you go forward by 10 years at a time, this whole pattern of Venus will move clockwise. Why does it move clockwise? Because it follows the Earth going around clockwise, the PVP orbit, right? So the PVP orbit is this blue one here, right? This is a PVP orbit. which we go around in 25,344 years. To show you that Earth actually moves, because it moves very little, I will put 1 second equals 1,000 years, okay? And then you will see the Earth moving, okay? The Earth goes, I'm clicking 25 times now, and the Earth will come back to where it started, 25,000 years,
Yeah.
okay? That's what the Earth does. And you will ask, what does the Earth revolve around? Nothing. This point here is, this point is virtual. You know what this point is? This is a point where Mars always passes. And
Right. That's like on that
that
other diagram. You see Mars go
and
right
that's
through
where
that
we
spot.
here. This diagram is what you want to look at now. Can you see this diagram?
Yeah. Yep.
All right. In fact, the orbit of Mars pivots around the center of the PVP orbits. I mean, imagine when I found this out. What have I done here? I've taken 4 screenshots from the Tychos and superimposed them. 4 screenshots with intervals of 6,336 years, which is a fourth of 25,344. 25,344. And then I just put this on here, put this on here, put this on here. And what do you see? This green dot, whatever, I mean, it looks like greenish, right? Yellow green. This is
That's
the point
the
where
Berry
Mars.
Center.
Hmm?
Is that the Berry Center?
That we need to rewrite some terms we have always been accustomed to. What is a barycenter in this case? I call this the secular barycenter of the entire system, and Mars is the body that always visits it. So Mars is a very important planet in this system. It is the one, it pivots, the whole orbit of Mars pivots around this little point here, which just happens to be 56.6 million kilometers, which is exactly the radius of my PVP orbit. And you understand, the PVP orbit is something that I have estimated with completely other ideas, parameters. I just looked up in the sky and calculated how much the sun would move if it went from Polaris to Vega, and I came up with this estimation. But then after a few years, I realized that Mars is always kind of going here in the middle all the time. Well, I mean, you understand? Mars has a very eccentric orbit, so it will not always pass here, but every time it comes closest to Earth, it's absolute perigee. It does it over long time periods of time. It comes very like the last time it passed very close to us. It was in 2003, on 28th of August. It was at 56.6 million kilometers, and then it returned in 2018 because it's a 15-year cycle it has. And it was just slightly further away, but the closest it can get is 56.6, which is just the radius of my PVP orbit. I mean,
Coincidence?
Is it coincidence? Is it coincidence? I don't know. So about retrograde motions, yeah. According to heliocentrics, the fact that our planets are observed to periodically reverse course, I mean, they go backwards, they seem to go backwards, is just an illusion of perspective caused by the Earth overtaking them, or vice versa. Let's see if this theory holds water. Here is how they explain why we see Mars going backwards. Yeah, so we should be going around the sun like this, and when we overtake Mars, which goes slower, then it will give you this effect that it goes backwards. All right. I mean, guys, I used to accept this thing. It made sense to me many years ago. Yeah, optically it could be. You're in inside lane. You're a horse rider overtaking another horse rider, and you will momentarily see the guy you're overtaking going backwards. All right, but it does not work. It does not work when you look at it closely. It does not work. Why? Because when Mars comes closest, you remember I told you it comes at 56 million kilometers, the closest.
Yes.
In 2003, it was very close. They said it has never come so close in the last 60,000 years as close as in 2003. So this was a very exceptional close passage. Well, the retrograde was very, very small in 2003. But then 8 years later, when it came on the other side, it was much, much larger. Well, that is completely contrary to the laws of perspective. If you want to try, you put your finger in front of your nose, look at the library down in your living room, and you move your head. When your finger is close to your nose, many books will move, many books. But if you stretch out your arm, your finger, many fewer books will move from side to side. So that's the laws of a very elementary law of perspective. But what we see with Mars is the exact opposite. So their explanation is trash. It doesn't work. And also, this is a Venus and Mercury. You know, an interesting thing that the average, the average number of days in which Mercury goes backwards is 22.8, and the average of Venus is exactly the double that, 45.6. So it's just to show that this is a Swiss clockwork we are having around us. The whole system is a clockwork, incredibly precise clockwork.
I mean, we probably talked about this before, but I just don't see how they haven't, how they're still going on the old system. Like, how can so many things be built on the old system? I just
It is amazing. The biggest question I have today is how come no one has realized these things?
Yeah, exactly. That's what I mean.
Easily computable things. I'm just, I'm stumped. I don't know why did I have to point out these things? It's the biggest mystery for me right now.
Okay,
but anyway,
the
136 resonance. I mean, look at this, Graham. I mean, the 136 resonance between our moon, Mercury, and Venus. I had to come up with this, but this is verifiable. This is the way it is. I mean, so they are three moons. Mercury and Venus are moons because they have a 136 resonance, just like the three first moons of Jupiter. They have a 124 resonance, and these three guys have a 136 resonance. So they are moons. Basta. Sorry, I interrupted you.
No, you didn't. That's okay. I was just trying to wrap my head around what the resonance meant for moons. It's to do with the speed and the spin of it. Not the spin, right? This
resonance?
Yeah.
The rotational
2.7 kilometers an hour. So the rotational speed of
if you are say you're standing on the equator of Venus, you will be moving at 2.7 kilometers an hour. Same with Mercury, we'll be moving at 5.4. If we stand on the equator of the moon, we'll go in 16.6.
See, I'd like to see that in miles because the moon apparently travels its diameter in a day. Exactly. Was that it, Darren? What was that? Was that it?
The moon travels its diameter in a day.
Yeah. Which was 200 oh no, I gotta find it again. I can't believe him. Yeah.
Oh gosh, we have
the moon's diameter is 216.
The moon's diameter is 3,400 kilometers, something like that. 3,400 kilometers.
9 times 24.
It's actually, I mean, it's in the book. You're gonna see. I've listed all this number. I don't have, such an incredible memory for numbers. Okay, 3, 4,
But
7,
the point was is that
4,
it
7,
resonated.
9
The point was it
kilometers.
resonated. The miles was connected to the hours. Is I think the point I was trying to make there. So it'd be interesting to see in miles for
But
the sacredness of the.
Please don't confuse orbital speed with rotational speed.
Right, right.
All right. And here we are talking about the rotational speed of each of these bodies, not the orbital speed, not the velocity they move in space. It's the speed of the rotations. You know. So we have to distinguish this. But our moon. I mean, let's now look at our moon. It's absolutely an exceptional moon we have. So we already know that our moon is a unique and exceptional lunar satellite because it is over 27% the size of Earth. There is no moon we know of that's so large in relation to its host. Okay, all the moons of Jupiter are far smaller than Jupiter. All the moons of Saturn are far smaller than Saturn. So, and then it revolves around Earth and rotates around its axis in 27.3 days in synchrony with the sun's actual rotation. Yes, the sun rotates in 27.3 days, just the same period that the moon revolves around itself.
The Swiss clock. I better just correct my what I meant by that. 216 is 216 is the number that Darren and I were looking at the other day on Malcolm Bendel's chart. But what it means is 21,600. But he's taken, he's looking at it as far as 216. So that's
okay. Yeah, it's a shame we have this problem with miles per hour and kilometers. Why did they give us two different measurements? Anyway.
Well, what it seems like is the world trying to go in the direction of kilometers, but some people are trying to hang on to these miles, and you wonder why. But if the Earth is moving at 1 mile an hour, I would argue, that might be why. It's sacred for a reason because the ancients knew that.
Okay, all right. I mean, I just want to choose one or the other. I'm not, in love with kilometers, or I don't hate miles, but it's just unfortunate that we have these communication problems about distances today. Anyway, here is why our moon matters. All right, it's a bit of a joke here. Our moon matters. It matters because, according to the Maya, the synodic period of the moon, which means the time it employs to return in front of the sun, is 29.22 days, the average one. We see it coming back today in our epoch in 29.5 days, but over long periods of time, it's 29.22. So that's one. We count that as one. 29.22 is one here in this relationship. 4 is Mercury, exactly 4. Mercury returns in front of the sun exactly 4 times longer than the moon. And Venus returns in front of the sun, from our perspective, in 20 times. And it goes all the way to Jupiter, 150 times. Saturn, 375.00, no decimals. And then Uranus, 1050. Neptune is an exception, 2062.5. I don't know why Neptune is. Well, Neptune is a bit strange anyway. And Pluto, 3100. So the synodic period of our moon is like, I call it the central drive shaft of the whole system. It's like a gearbox, you have a drive shaft, and it has exact multiples driving all the other planets in our system. Again, how have now no one pointed this out? I don't know.
Well, we've got some other buddies that are definitely getting close with some moon stuff to some crossover, I would say.
Which begs to ask, what? So how can it be such a weird ancient? Like, how can it be you know, a lot of people say it's man-made or it's fake or it's more of like a machine than an actual moon. But if what you're saying is true, Simon, then this would be the you know, required for the whole solar system to work. Like the moon should have been here all along. Like,
what do you mean? That? Sorry, I didn't get the point you were making.
You know what I mean, Darren?
Yeah, I get it, but yeah, no, yeah, I get what you mean. Yeah, for sure.
Can you explain it in a better way?
Well, Simon's not entertaining a solar system without a moon. This is the difference. So it's going to be hard to cross that thing.
Yeah. But that's what I'm saying is his theory will blow sort of those other theories away in a way, because the moon's sort of been an important part of this all along, not just an added after effect to affect the Earth somehow. Like it's really intertwined with the whole system.
I mean, just remember, if you allow me to repeat, that the moon goes around, it does one orbit returning from the sun in the same time that the sun orbits around its own axis. So there is obviously an incredibly close relationship between the sun and the moon, whereas heliocentrists say that the moon is just a moon, an appendage of the third planet's Earth going around. You know, isn't it a special thing? I mean, how can you continue to say that the moon is just an appendage, you know, a random appendage of the Earth that goes in the third lane around the sun, when the sun rotates around itself in the same time that the moon rotates around itself, and its synodic period is also 27.3. 27.3 is the number of days the moon employs to rotate around its axis, just like the sun, plus around in a synodic period, which means when it returns facing the sun. I mean, it's completely interlocked. It's the sun and the moon are completely, you know, like father and son. It's not the case with any other moon we know of, right? So,
in our solar system.
In our solar system, of course, yeah. We're talking about a solar system right now, right? So the most lunatic Copernican absurdity is actually this one. You know, we can see it every 27.3 days. This is funny. This is another cartoon I made. This is like they're telling us that the Earth and Moon system is going around the sun, right? Well, let's see. We start here. So one day we see the moon pointing at a given star. Let's call it star Madonna. Okay, whatever. Well, after 27.3 days, we will see again the moon in front of the star Madonna, and again and again and again. It will always come back in front of star Madonna, even from here to here, and that's 300 million kilometers. Again, 300 million kilometers of lateral displacement. It's absurd. Why? How could this ever happen? These are, ladies and gentlemen, absolutely parallel lines. If you go on an official heliocentric simulator, you will see parallel lines. But of course, they will say, no, it's because the stars are so far away, so there will be no detectable parallax. What? 300 million kilometers will not do any change in the position of the moon in front of a star? I mean, ridiculous. So the moon's oscillation. Oh, this is a bit more complex to wrap your head around, but it's in the book, and I highly encourage you to understand it, because it's absolutely amazing. It confirms what I'm saying is that the Earth-Moon system moves every year by 14,036 kilometers every year. Well, it just happens to be the oscillation of the moon's perigee 14,036. And the oscillation between its perigee and its apogee is exactly 3 times that, 42,108. Is that another coincidence, gentlemen? You will have to tell me. This is yeah, it's taking up. It's piling up. And when I discovered this, I honestly fell off my chair. I really didn't expect to even show that the oscillation. You understand oscillation? Many people. I realize that many people don't know what oscillation means. It's just the variation of its position of a moving thing. The oscillation is when it goes back and forth. All right, the oscillation that I can absolutely show that in this system is, and you know, these numbers are official. If you go to sites that track the moon perfectly, they will tell you that the difference of from one perigee to the other is 14,000 kilometers, and the difference between a perigee and an apogee is 42,108. Exactly 42,108. Amazingly enough, I mean, really, the exactitude is absolutely flabbergasting.
And of course, people can get that for free at Tychos.space.
Mm-hmm. This is my favorite. I mean, when we're talking about the moon, this is my favorite proof of the Tychos. The exeligmos. Now, I know no one will have heard of exeligmos. What the bloody hell is exeligmos? What is exeligmos cycle? Well, it simply is, well, what we are told, what is being observed, what has been observed is that if you have a solar eclipse one day, to have that the solar eclipse occur again over the same place of Earth, you will have to wait 54.1 years. 54 years and 33 days, exactly. That will be when a certain solar eclipse will reproduce itself identically on the same place of Earth. But after 54.1 years, it will be 1/12th, a slice of 12 of this cake will be 1/12th difference, but it will come. The same solar eclipse will occur. For instance, let's say on the in Rome here. Let's say I'm Rome. On a certain day, I will see a solar eclipse. I will have to wait 54.1 days to see it again over Rome. Okay. No one has ever explained why the exeligmos exists. Okay, no one has explained why is it 54.1 years. Well, you know what? In 54.1 years, according to the Tychos, this disk, which imagine this is a compact disk. Okay, this is a compact disk. This is the orbit of the moon. This is the Earth-Moon system. Okay. And we call it a compact disk. To make this compact disk move by 1 unit from here to here, I mean, you see, just from here to here.
Yeah.
And accepting that the system moves at 1 mile per hour, it will exactly do this in 54.1 years. 763,000 kilometers is the diameter of the moon's orbit, and we will cover 760,000 kilometers going at the speed in 54.1 years. All right, did you get this? Do you understand? I mean, we are moving from left to right. Okay, this is Earth-Moon system. To go from like this point to this point, going at 1 mile per hour, we will employ 54.1 years, and that's why the exeligmos exists. There is no official explanation for the existence of the exeligmos. And the exeligmos is simply three Saros cycles. Saros cycles, people have heard of, I guess. They are exactly 1/3 of 54.1 years. But so it's again 3 to 1, 3:1. The 3:1 ratio is everywhere in our system.
But how? I guess I don't understand the relevance of that. If you're just measuring the the length of time it takes for the Earth and Sun to line up again like that.
The relevance of these,
they just don't have it. They don't even address that as a question or a problem.
No, I mean, no one is saying that we're moving slowly from left to right like this. This is just my.
Oh, okay. I see what you're saying. It's based on your speed. That's why
it's based on my speed.
Because if it's based on their speed, what's their answer for it? If it's based on
they don't have. I mean, look, I've been trying to look everywhere. Why does hexagonals occur in the heliocentric system? There is no rational explanation. It just happens. We know it happened. We observe that. Okay, but why does it happen? What is there a geometric pattern that makes it happen? Well, here it is in front of your eyes.
Oh, I see. Okay, I get it.
Okay, here it is.
Yeah.
Okay. So about the NLM and a man's yearly path. Well, this is really. I love this. And the NLM was maybe the thing that made me start looking at astronomy, really. Because the NLM was something that was... All the old globes you had in the living rooms had this 8 thing drawn upon it. You know that?
No, I didn't know that.
All the old globes. I remember as a kid, I remember seeing one. I said, "What's this, Daddy?" He couldn't explain. And so, what the bloody hell is this? Actually, they don't print it anymore on the modern globes, probably because they can't explain it.
No, but now people are taking pictures of spots and stuff in the sky to come up with their own analema, right?
Yes. Yeah. No. You can picture it. No. You can very well. This is an analema taken by a photographer. Okay. This is what the sun does in 1 year. In June is on top, of course. The sun is highest in June, and in December it's lowest. Fine, good, okay, no mystery there, because the Earth tilts. But why does the analemma doesn't do an H shape, so it moves laterally as well, from side to side? And why is it asymmetric? Why is it much shorter here and longer here?
Yeah, when the seasons are the same.
Yeah. So here's why. I dare say. I call it the man's yearly path. A man, I mean, you imagine now you're an astronomer, okay? You're an astronomer in London, Darren, okay? Where you were the other month. You were standing in London here on March 21 on a given day, on a given year. And you look at the star, okay, with your telescope. Well, in April you will be here. In May you will be here. In June you will be here. And so forth. And in 1 year, you will have physically, your body will have done this. Because since we are rotating once a day and proceeding slowly forwards and covering a little more than the diameter of the Earth itself, we will do this trochoid. Anyone standing still in one place of the Earth for a full year will do this. It's a trochoid. It's a prolate trochoid. So, since heliocentrists don't know this, they've had so many problems understanding why the stars look like they're doing this, because the stars they look at do this trochoid. I mean, let's show immediately. I want to show you immediately. This is what Vega does in 3 years. Bing, 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 bing. You see, this is a trochoid. But they say, oh, it's because of aberration of light, or some funny, incredible things they've had to come up with to explain why all the stars are seen to move a bit like this. Some a bit, because it depends on where the star is in relation to the angle of the star in relation to your position on Earth. So, okay, so this is absolutely crucial. The man's yearly path explains so many things. It explains the dilemma. Why? Because since you, Darren, you're the astronomer now, you're looking at the sun, you can picture the sun tick, 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 in these months. And there's a 3, a ratio of 3, and it will go in one way. And then it will go the other way at the ratio of 1, but backwards. Okay, backwards. Okay, so it's 3 to 1, 3 to 1. This is why the dilemma will appear on your photographic plate. Because you will have done this. Your frame of reference is a trochoidal one, or continually looping like this. So that's simply why the sun will look like. But the sun is obviously not doing this for real. But mind you, that's why we need the equation of time. Do you know that our clocks are only exactly on time with noon 4 times a year? That is on December 24, Christmas night, for some reason, April 15, June 16, and August 29. These are the only 4 days in which the sun will agree with your watch, with your clock. Exactly. Otherwise, it will fluctuate by 15 minutes, plus 15 or minus 15. Actually, plus 16 and minus 14. It will fluctuate with your clock. Our clocks are never really on time with the sun. They're not, because of this problem here. We are always going around this bloody loop. And here again, this is a similar diagram, but here with more exactitude, I show you that August 29 and April 15 just happen to be the intersection of the dilemma. Well, what do you know? These positions of the astronomer taking, or the astrophotographer, will be exactly when April 15 will be a moment when it goes straight, because this is motion of Earth. It goes straight this way, and August 29 will also be a moment when it goes straight this way, without any, angular deflections. So that's why August 29 and April 15 is the intersection of the dilemma.
Why are they offset from the solstices, I wonder, or the equinoxes? I wonder why it's offset a little bit.
It's a little bit offset because the equation of time is just it's a mathematical gimmick made to make our clocks work as well as possible. Our clock says our clocks go around at the same speed all the time, right? Our clocks. I mean, we can't make clocks that slow down or speed up. So they've made interpolation. They made it's called the equation of time, and they explain how they have come. And they admit that it doesn't solve the problem. I mean, the sun is never on time with our clocks. Only 4 times a year. Only 4 days a year. The clock is in time with the sun. And here it is explained graphically. So here is, okay, we see, why the stars move like this. All the stars move like this.
Darren, was there another part of the Tychos that you wanted to explore as far as one of the big things?
No, I think it's about time to wrap up. I was just going to ask Simon if he had any last things he wanted to show before again, people can get the book at tychos.space. They should head there and check that out. But is there any last things you want to show before we wrap this up, Simon?
Well, no, I think we have covered quite a few things, and I just will recommend people to look at the parallax issue, the stellar parallax, because which you see here,
the most confusing part.
Yeah, it's the most confusing part. It isn't really. It is about the difference of thinking that we are going around the sun, or the sun going around us, and that will explain why we see negative parallax. Whereas only a positive parallax can ever occur in the heliocentric system. But what all the astronomical tables have is 25% positive and 25% negative parallax. And this is physically impossible, and really physically impossible. But it's perfectly explained why they see this in the Tychos. Because since we are going slowly in a straight line in the middle of a rotating, the sun is rotating around, revolving around us, we will at times be able to see out of our if we think we're going around the car with the car around our orbits, we are in a car. At times we will see the stars in the left-hand window, and at times in the right-hand window. This will not happen in the heliocentric paradigm. We will always see the stars in a right-hand window.
Oh, I see.
You see?
Yeah.
So that's why we have, half of the parallaxes are negative, or positive, but no one understands why. And it's a huge issue with in astronomy today. They don't understand why they're seeing so many negative parallaxes.
I think Charles Fort was pushing back quite a bit on that, even when he was roasting the astronomers in a couple of his books.
And
Simon,
I'll
go
finish off with the fact that astronomers will tell me, yeah, but we see the positive parallaxes are usually larger than the negative ones. All right, but here it is explained. Bessel, the famous Bessel, who apparently was the first one to see the first parallax of a star, the star Cygnus. The first time he reported a parallax, it was negative, as they found out in an old astronomy book. So he probably used this period of time to what? This is Cygnus here, the star Cygnus. He probably used this period, which goes backwards. And oh my God, it's going the wrong way. I didn't expect the parallax to be negative. But then later he saw it during this period from March to July. And oh, good, finally it goes positive as expected. So this is what he published, the green observation. But the red one was discarded. That's how they go about, when they have this confirmation bias, those heliocentric people.
The rest of the world.
Yeah.
Simon, this has been great. Is Tychos.space? Is that really the only? That's pretty much everywhere everyone has to go, right? TYCHOS.space.
Yes, that's pretty much where you'll find everything. You'll find a link to the Tychos forum. If you'd like to come, you're very, very welcome to come and discuss with us. We're a small community for now, but very, very smart people there, and we think we are on the right track. So please join us.
And play around with the model too. I mean, people can play around with the model. It's amazing. I mean, you can.
I think it really is the most user-friendly simulator of our solar system I've ever. I've been playing around with other models in earlier years, and I always find it difficult to understand how they will work. But I think the Tychosm is very, very user-friendly. And Patrick, my partner in crime, has been doing an amazing job making it easy to operate. And remember, the Tychosm shows all the planets going at constant speeds and in uniform circular orbits. Exactly what all the astronomers of ancient times were hoping to achieve. It was the natural idea of how planets would move would be to finally find a way of showing that they go at the same speeds all the time. Why would they slow down and speed up, like Ekpro said? Why would they go in elliptical orbits? Well, there's no need for that. The Tychos has no elliptical orbits. Of course, it has trochoidal orbits, but that's, as I showed you, it's just a circular thing that goes around another circular thing. But it has no variable speeds. Yet it works perfectly and agrees with all the astronomical tables you can find. And all the solar eclipses, all the transits of Mercury and Venus in front of the sun. It's incredibly accurate already. It's still a work in progress. It's not perfect, but it's pretty damn accurate. I can assure you. You can compare it with Stellarium, the famous Stellarium simulator. The bodies are where they say also, and they are completely comparable. So thanks for inviting me again, guys.
Yeah, thanks, Simon. This has been great. We encourage everyone to head over to tychos.space and check that out. And we appreciate you staying up late and coming back on the show now that you got the slides together. You know, we might end up doing this again down the road again, but I encourage everyone to go check that out for sure. And Simon, you have yourself a great night over across the pond. We appreciate you doing this on your Saturday night.
Thank you. Thank you. It's been honor to be invited again.
All right. Ciao for now.
Thanks, buddy.
Ciao.
Good to see you.
Yep. Take care.
And that was our chat with Simon Shaq. What'd you think? I'm curious to think what you think, because I'm trying to get you over on this one.
Yeah, I'm a little farther. Yeah, a little farther for sure.
A little closer, getting a little closer.
It just takes a while for me to wrap my head around this kind of stuff, but
it is complex stuff for sure. Of course, big thanks to Simon for coming on the show, for taking his Saturday night across the pond to spend it with us. Big thanks to you guys for listening. Even bigger thanks if you are one of those supporters over at grimerica.ca/support. It's the only way we can do that. Or do this. Of course, head over to grimericaoutlaw.ca if you want to check out our other podcast, and adultbrain.ca for the audiobooks, and contact at the cabin for the trips. Other than that, we love you guys. Thanks for listening, and we will see you next week.